carbonyl. Right? So if we number this, I'm not going to, these aren't the actual numbers, but we call it 1, 2, 3, 4, right? That's carbon 1, 2, 3, 4. If you look at the structure of citrate, right, it's 6 carbons, but it's branched. So citrate, what it really is a 5 carbon chain. And when we look at this, we see it as it's a symmetrical molecule. We have a central carbon with an OH group, a carboxylic acid, and 2 CH2COO groups, right? So even though oxaloacetate, so this it's an 8 carbon molecule, the oxaloacetate is itself asymmetric. The product itself becomes chiral. And so you keep all those facts in mind, you don't have to necessarily commit the mechanism to memory to be able to draw the structure itself. The addition of the acetate from a chemical standpoint, the acetate to the oxaloacetate favors the maintenance of that diester bond, which prevents hydrolysis of acetyl-CoA 2 acetate, right? Going from acetyl-CoA to just acetate is metabolically disfavored. Citrate synthase, dimer, with ordered binding. In order for the acetate group to be transferred from acetyl-CoA, this enzyme must bind oxaloacetate. In fact, must bind 2 oxaloacetates first in order to close it in to an acetyl-CoA catalytically competent site. Right? This prevents, if acetyl-CoA were able to bind first in an active state, that would enhance the likelihood of just breaking the thioester from CoA. This, binding OAA first, binding oxaloacetate first, enables, when the acetyl-CoA bind, to transfer it to something useful, to those oxaloacetate sites. Is there an enzyme that we talked about in metabolism that has a similar strategy in terms of its substrate binding? No, you got it. No, that's not. Obviously, it's a leading question. There is one. You remember what it is? Ordered binding, preventing disfavored hydrolysis, wasting of an active wasting of a substrate. We go back to the very beginning. Hexokinase, right? So hexokinase binds glucose and ATP. And in order to prevent the ATP from just being burned, it has to bind glucose first in order to bind ATP to transfer the phosphate. So you see the similarity, right? ATP valuable, energetically valuable. Don't want to use it up without having a benefit to it. So it doesn't easily use ATP up until something for the phosphate to go to, glucose binds. Citrik synthase. Acetyl-CoA is valuable. You don't want to burn it until it can be used for something. Used for something by transferring to oxaloacetate. Oxaloacetate binds first. Again, I'm not going to go through the deep electron pushing of this, except to say, we can see the tautomerization event that we talked about. Notice there's two histidines and an aspartate are necessary to catalyze this. It's all acid-base chemistry. For more organic chemistry inclined, this is a Claisen condensation mechanism. It's different from the aldol mechanism. But again, that's our first step. So let us, as we did before, start to put these in order. And the way I'm going to do this is go black. We have our coenzyme A with its acetyl group, right? So we've gone through glycolysis, we've gone through pyruvate dehydrogenase, we're looking at acetyl-CoA now. So we've got those two things. we have citrate synthase. And then this gets us to the formation of, right, so this. And as you're committing these reactions to memory, always make sure you're counting carbons, right? We should be at 6 carbons. Tricarboxylic acid, so 3 carboxylic acids. And actually, let's go through the delta. We're going to go through the delta G's with citric acid cycle again, because a thioester has been cleaved. I'm actually going to fix that. Make sure the sulfur's on it. As the thioester is being cleaved, right? That's a high energy equivalent. Thioesters have free energies close to ATPs. So we can imagine this first step as being very exergonic, and it's around, citrate synthase has a delta G0 of about minus 30, 0.4 kilojoules per mole. If we want to think about the reaction of the citric acid cycle as a whole, it's really about, again, this is the total oxidation of those carbons. So we have 2 carbons, so 4 electron pairs. So we've got to transfer those 4 electron pairs out of those carbons through this process. The next step is an isomerization. Specifically, it's the transfer of the OH group from the central carbon, from carbon 3 to carbon 2. It turns citrate, so against an isomer, it's the same formula, but it turns citrate from that non-chiral molecule, non-chiral compound, into a chiral compound, right? Because now you have this carbon that has 1, 2, 3, 4 different things around it, so that's now chiral. Which means citrate has the ability to be made chiral by isomerizing. The chemical term for that is prochiral, right? It's not chiral itself, but it can be made chiral through a chemical reaction. The enzyme that does this is called aconitase, and aconitase does this isomerization. So this is not the same as the isomerization reactions that we saw in glycolysis. It's a different chemistry because in glycolysis we were seeing 1-1 proton transfers, right? We're seeing movement of a carbonyl to an adjacent alcohol or back. In the case of citrate, we're seeing a hydroxyl group transfer. So in this case, how this enzyme does this is by actually just clipping off the OH in terms of a dehydration, and then just adding in a different hydroxyl group from a different water at the appropriate carbon, right? The dehydration creates this alkene, right? And so the alkene can then be added on either carbon, and the stereospecificity of the active site not just favors which carbon it adds, but also which direction it goes to. So theoretically, that OH can move to the other carbon here, right? Because if this is a prochiral molecule, there's no chemical difference between that and that, so theoretically this could move that way or that way equally. But again, what's our constant point with enzymes is that enzymes are able to, through their structure, control the stereochemical outcomes of the products they make. And in the case of aconitase, it consistently and irreversibly transfers its OH to what's called pro-R arm of the citrate, not the pro-S arm of the citrate. We also introduce what's commonly used as a redox cofactor. In this case, it's not a redox reaction.